In this work, we introduce a novel meta-updater, an effective module that controls the online update of trackers with little extra computation burden. The task of long-term single-object tracking has more challenges than the short-term counterpart. The length of frames is much longer, the target disappears frequently, and more deformations and cluttered background occur. So the online update of long-term tracking is much more difficult. To control the online update of the tracker, we propose a novel meta-updater. It can accurately judge whether the current frame is suitable for updating the parameters. In experiments, we observed several kinds of information that is useful for the control of online update. The first one is the geometric queue of the target. As shown in this figure, it indicates the position and shape of the target. The second one is the discriminative queue. It refers to the confidence map or response map predicted by the tracker. We also observed that the appearance queue can be helpful as well. The image patch of the tracking result in each frame is used as the appearance queue. However, the information in a single frame is not enough to judge whether the current tracking result should be used for updating parameters. For example, this figure shows the confidence maps outputted by item on a video sequence. We can see that it's hard to make decisions by the value of score or the shape of the response map from a single frame, but we can observe some clues from the history curves. So we should embed these cues with their history information. It's obvious that if we utilize their sequential information, then we can get more messages, such as speed, trajectory, appearance changes, response map variations, and so on. This is the framework of our meta-updater. The inputs to the LSTM are the cues mentioned above, collected in each frame, and the output is a single feature vector of the last time step, which is further processed by fully connected layers. The final output is a single score that indicates whether the current tracking results should be used for online update. Visualize the training samples of our meta-updater. The top two rows are positive examples, and the bottom two rows are negative ones. The meta-updater is trained in an iterative way. The tracker first runs on the training set of LSOT and collects the training samples it uses for online update, along with the confidence scores, the bounding boxes, and the response maps. Then we use this data to train our meta-updater and embed the meta-updater back into the tracker. The new tracker runs on the training set again to collect meta-updater's new training data and then training the meta-updater correspondingly. We do these procedures iteratively until the meta-updater can work with the tracker perfectly. This figure shows our overall framework. The meta-updater controls the update of local tracker and verifier. The other sections are similar to current long-term trackers. These two tables show our performance on two popular long-term tracking datasets. And these are the results on another three popular benchmarks. We further embed our meta-updater into three popular short-term trackers, and their long-term performance is improved by a large margin with little speed sacrifice. The performance of the IMP can also be improved dramatically. We also have embedded our meta-updater into other popular trackers, and all the codes have been released in the link of this QR code. Thank you.